Okay. Well, first of all, the next several homework assignments are up. I think they'll take you through all of next week and all the week after that. It might even be into Tuesday of the week after that, something like that. So it gets you through almost all of the next game while we do some other stuff in class. And then yesterday, so make sure you check those out because the first one is due on Tuesday. So last time we were looking at procedural generated stuff, right? Now, generally speaking, if we were to kind of point out some pros and cons of procedural generation, what do you think is good about procedurally generating things? What are the perks of that?
If you have a lot of repetitive stuff to do, it takes some of the load off you as a game designer.
Okay. So, and with some specifics on those things, they kind of almost need to be geometric to some.
Yeah.
So it kind of needs to make sense that it's not going to require that human touch, right? Almost like there's a level of precision that's calculable. I think that sounds like the word calculable. Yeah, let's go with it. That would benefit from doing a lot of math, where it might kind of drive a human kind of crazy. So it's almost like a two-level thing there, where on one hand it's going to maybe make us be more precise. But on the other hand, is actually going to make our lives easier, like you said, where you don't have to sit there for 4 hours and do something. And something we're going to see today is it also allows us to be more generic. So like I think last time I think we started building our prefab for a step. We're going to start today and look at a procedurally generated staircase. Well, you might have staircases throughout your application. As an example, we're just picking some stupid example that might exist in your game, or maybe it's a ramp or whatever it is that has a certain length. That might even be a better example where you have, you take a plane and you programmatically stretch it to the right length, right width, and then rotation, and then you can anchor it off of something along those lines. In any case, it will make our lives easier and potentially more accurate in certain situations, and also allow us to have something that is almost like the definition of a function version of procedurally generated objects. So we can have staircases in 5,000 different places in our game. We only need to write that code once. Make sense? Okay. So we might say pros, easier for designer, reusable, it's reasonable, and potentially more accurate, or at least keeps programmer sane, something like that. What about cons? What are the negatives of procedural generation stuff?
It takes some time, beforehand, before you can start.
Okay, yeah. So potentially, let's just say potential time delay. What else?
It has to be exactly the same as the other one. Well, never mind.
Well, but I think what you're getting at is it must be calculable in some way. Whether you're dealing with the exact same prefabs, you're dealing with the exact same collection of 3 prefabs, or somewhere in between, it has to be something that you could articulate in an algorithm, right? So must be able to articulate, let's call it layout algorithm. Anything else? I might say potentially more generic look. You have less of that artistic ability when you're laying it out by hand. This way, you have to almost use maybe simpler, blocky type things, or even if you went fancier, you really needed to think it out ahead of time, or if you needed to make it look really cool or really like, I don't know, artistic, let's say, you really might have to do almost a hybrid approach where you design like in quarters or something in real life and then repeat some stuff, something like that. So some potential pros and cons. Punchline there being it's not always the right tool for the job, but sometimes it's a reasonable tool for the job. I think last time we mentioned a kind of a famous-y game that really, it kind of was famous for its leveraging of procedural generation. That was that game No Man's Sky, which my understanding is sort of kind of making a comeback now. Is that a true statement?
That was like a little bit.
Huh?
Like a little bit was.
And then it stopped again?
Yeah.
Oh, was it bad again?
Well, I don't think so. They made like a couple like changes to the game that made it a lot more playable. Like I think they had like you can actually have multiplayer. Like you can like meet up with like
find other people.
Yeah, basically, but and they made like a lot of changes. They made there's like more things to do in the game and stuff like that. But like it was only like really targeted for like the people who already really play it. It's like
it improved their experience.
It's like it brought like those people back, but I don't think it brought too many like new people.
Gotcha. Because that game, didn't they like pre-sell a whole bunch of copies of that game and then they had to refund a whole bunch because of false advertising or something? Like the game didn't deliver what they said that they were.
Yeah, a lot of people weren't happy.
Yeah. Did you play it?
No, but I've read a lot into it because I wanted to.
I see.
I learned.
Oh, so you weren't a pre-order?
No.
Yes, I had to be honest, actually, I think I might own it. It's not bad that I'm not even sure. It actually is bad that I'm not even sure, isn't it? Yeah, because I kind of recall playing it for a little bit after it came out, and I don't remember whether I was playing the one I bought or if it was like a friend of mine who said, log into my Steam and and try it or something. I don't recall. But I kind of remember it being somewhat interesting for like maybe a half hour or something, and then you're kind of bored.
Yeah.
Aren't you like repairing a ship or something at the very beginning of it?
Basically, you're like on a planet and you like try and like survive and use like resources on the planet.
But you were like shipwrecked.
Yeah.
So you're like repairing your ship, I kind of recall, or something like that.
Yeah, and then you go to the next planet and then it just goes again.
Yeah.
Same cycle.
Yeah. So, but I remember getting bored before I really got to do anything. I never even got off. I didn't even come close to getting off the planet. Yeah, I think I maybe found like a thing for like one of the panels on the ship to like fix it. And then I was just walking around and just seeing the same stuff over and over again. So that's kind of an example here of the whole procedural generation thing is you can get lots of terrain, let's say, very quickly, lots of stuff very quickly. But unless you make a very interesting algorithm, you might not necessarily have real interesting terrain. You can maybe even think about it from a game design perspective. Maybe you use it for like tree placement, something like that. At some point it becomes a little bit repetitive, or maybe if you're doing random placement, you just get this like weird patchwork of trees in this like one kind of area, and then everything else is barren just because of the, unlucky random number generation or something like that. So who kind of knows? All right. So I think last time we created a step. So this guy looks like this. And what we want to do is we want to kind of have we have this empty game object here. This is going to be our stairs. And what we want to do is we want to be able to attach a script to this guy and have it, maybe we can give it a couple of variables that we'll play with, but have it effectively generate a set of stairs from where that guy is. That makes sense? So I'm going to leave this out here for now because we're going to have to use it for some of our, what's the placement going to be, how far down and how far over, or how far down and how far over we need to put a step to make it look like a step. But let's go ahead and start building this script. So here's our gen stairs. I'll go ahead and throw it onto my stairs empty game object that we're using for our anchor. We'll open this dude up. All right, so now we need to go ahead and make sure this guy has available to it our building block, right, for our stairs. So we're going to have to give him access to our prefab. So what kind of public object am I going to create? What type of public variable do I need in order to, oh, well, I already gave it to you there. So we're going to need a public game object, right? We'll call that guy a step. And then also a variable is going to keep track of the number of steps that we want to generate. All right, so let's go ahead and connect those up out here. So I'll click on my stairs. Here's that initial script. I'm going to give that guy my prefab for a step. And then maybe for this first one, why don't we say 5 steps? Something like that. All right, so then we want to think about what steps are going to look like. So I'm going to make a copy of this guy. I was going to make a copy of that guy. Do I have another one? I think we actually have, yeah, we do. We have multiples there. All right, so does this look about right for a step down? Call it close enough. All right, so this dude is at, here, I'm actually going to do -4, -1, -1, just so we have kind of a starting place that's easy to work with. Slide this over a little bit. Something like that. All right, so that took us to a negative. So y was that a, and let me try this. Let's see if it's a -4, a -1.5, and a -2.5. That too big of a drop? It's too big of a drop. So let's say this is a -1.3 and a -2.4. So it's putting it higher up. So I need to look at this from a different, not from that angle. All right, that might be the best angle we're going to get. So we have no rotation on these. So this is my original step. This is my, well, actually, this was my original step. This is the guy we're trying to put right underneath him. All right, so -3.5 maybe there. 3.7. That looks pretty decent. And then height-wise, let's do -1.3. 1.4, too much. 1.35. Let's just do 1.3. And then Z, negative 1.5, 7, 8. See what a 2 looks like. Probably too much. Doesn't look bad. 0.9. That look like a step-ish. So we need to now look at the offset between these. So wherever our top step is starting, on X, our position is going down by, so this was a negative 4. It's getting, it's increasing by 0.3 if we're going in the downwards direction, right? So let's mark this up. So we're going to say X increases by 0.3. So wherever that first guy is.
Couldn't the Z just be the same for the 2?
I don't think it didn't look right when we had it as the same. That would make some sense, actually. Let's look at that from straight up above. Yeah, I think it is. Z doesn't change. Just was looking funny. And Y is...
I think the Z is like the Z is like the constant between the 2.
Yeah, actually, but we're laying this out. No, this is laid out wrong. Because if I'm looking at it straight down, let me make sure I'm looking at this from above. All right, if I'm looking at it straight down, this guy here is my which step? So this is step.
That's the original.
Yeah, I'm going to drag this under stairs here so we can move stuff around. And I'll drag that guy in there. So here's our stairs. I'm just going to kind of, and I'm going to move that outside of that. They shouldn't be connected anymore. Oh, this is my stairs. So I need these guys to be shifted. Just pretend like that's good there. So now if I'm looking at it that way and I look at it on the Z plane, that's going down that way. If I look at it on the X, that's stepping down that way. So yeah, this is right. Yeah, that's why Z doesn't change, because we don't want one of the steps to be farther or closer to us in the scene. Okay. So the difference between the Y and, well, the Y is going to be a minus 0.3. Decreases by 0.3. And Z stays the same. All right, and this decrease will end up being an increase if we change the direction of our stairs. All right, so let's mark those things so we know where our stuff is going. Then inside of start, we're going to do something number of steps, number of times, right? We're going to do something number of steps, number of times. So we're going to say for int I is equal to 0, I is less than number of steps, I plus plus. Okay. Oh, just to stay consistent, I like saying this dot number of steps, but whatever, it's a little faster. Okay. So now what do we want to do that number of times? Well, we want to instantiate a step at the right position, correct? So we're going to start off with a vector 3. Now remember, we have put this guy, we've attached this script to our kind of our anchor point, our empty game object where we want our stairs to start. And this kind of goes back to that concept we talked about. We just were kind of playing with it. This idea where if I click the stairs here, our stairs game object, and then I drag that around, everything comes with it, right? So the stairs empty game object is actually a parent of the sample steps that we have here. So that means when we give a location for the original step, it's actually going to be positioned relative to the anchor point. So if I say 0, 0, 0, for example, the starting point for this guy, which is would be a vector 3 for his position, that's going to be relative to where the parent is, anywhere in the scene. So 0, 0, 0 won't necessarily put it in the middle of world space. It'll put it relative to the parent's location. That makes sense? All right, so we're going to go ahead and we're going to have our starting. So we'll say vector 3 curpos is equal to a new, actually I think we could just say vector 3 dot 0. So that's going to be 0, 0, 0. All right, so that's a starting point for our vector 3. And remember, structs are passed by value, so now I can make changes to curpos, and that's not going to break the default vector 3 0 value. Okay, so I have a 0, 0, 0. All right, so very first time through, I'm going to go ahead and instantiate a step at position curpos with a default rotation that that would be the, how do I get the default rotation? If I'm dealing with rotations, what's the word that pops into your mind? Quaternion. And remember what the function was for, or the field was for a default rotation? Yeah, it was identity. All right, so, and I'm going to ask you a question about that here in a second. So the first thing we're going to do is we're going to go ahead and instantiate this guy. Now, do you see a need for actually storing our individual steps? Like, do we want to keep them somewhere? Or once they're on the screen, are we okay? Are we going to have to, the question is really, do we need to manipulate steps after they are in existence? Or once they're on the screen, are we good?
Should be good.
Okay, so let's start off with that. Then we'll decide if there's a reason to maybe change our steps. Okay.
Unless we're having like Harry Potter.
Yeah, I was literally thinking the same thing where the steps actually change places. So we can give ourselves that ability, but let's start off keeping it as simple as possible, right? All right, so we're going to go ahead and we're going to call instantiate. And remember, there's a whole bunch of different versions of this guy, and we want the one that takes a vector 3 position and a quaternion rotation. So what are we instantiating? We're instantiating a step. Where are we instantiating it? We're instantiating it at curpos. And what's the rotation? Quaternion dot identity. Okay, now this quaternion thing here, what kind of programming animal do you think that is? What is quaternion, and why might you suspect that? I'll get you started. It's the name of a class. Why do you think it's the name of a class? When you look at code and you see something like this, and I'm telling you this guy is the name of a class, why might you assume that's the case?
It's like quaternion dot, like, then it's using an identity like similar to like this dot number of steps.
Typically, it's because of the capital letter. Yeah, capital letter usually flags something as being a class. Now, presuming this is a class. Now, keep in mind, this is just a guess. In fact, I think I just saw that this actually is not a class, but let's just take it down the road here. Okay, so assuming that we've made a good guess here that this guy is the name of a class because it starts with a capital letter. Identity, actually, yeah, it actually is implemented as a class. Kind of weirdly defined, but because it's part of Unity engine, but that's okay. All right, so if this quaternion is a class, what must identity be? What are the three things that can live inside of classes? Starts with a C. O. N. S. Constructor. Okay, fields, methods, and constructors are the three things that live in sides of classes, right? Now, we know this isn't a constructor, right? What would we see if this was a constructor? What keyword would be present somewhere very close by? New keyword. You 250 people, this is fresh. This is very good. So the new keyword would be very close by if this was a constructor. Okay, it's not one of those guys. If it was a method, what would we see? Parentheses. We see a parameter list. So this guy must be a field, right? So a field is a variable associated with the class. Is it a class field or an instance field? Okay, tell me why you're wrong.
Oh, it's going.
Okay, so presuming this guy is the name of a class, this guy must be a class field. We know he's a field because we don't see the new keyword. He's not named the same as the class because constructors in Java and C# are named the same as the class. That's not a full truth across all languages though. Okay, but we don't see the new keyword, so it's not a constructor. We don't see parentheses, so it's not a method. Therefore, the last guy out is the field. So he must be a field. Specifically, what kind of field? He's a class field because we're calling him with the name of a class. That makes sense? All right, so that is the punchline for that stuff. All right, so we're going to instantiate a brand new object. What kind of object? A step. Where are we putting him? At curpause, and then we're going to keep him at the default rotation. All right. So now what we're going to go ahead and do is we are going to modify our curpause vector 3 so that the next time around we put this guy in a new place, right? And what do we want to do? We want to increase the x by 0.3. So we're going to say curpause dot x plus equals 0.3f. And we want to decrease the y. Curpause dot y minus equals 0.3f. So that the next time around, it will instantiate this guy in a new location with the same rotation over and over again. How many times? Number of steps, number of times. Make sense? All right. So having those things there, I can now go into go back into Unity here. And I'll dump my couple of extra steps that I built in here. All right, and we did have our stairs inside of our walkway because we kind of decided that made some sense, right? So now what I'll go ahead and do is we already have our stairs. It already has the script. We said we want a step. We said we want 5 steps. So now if I hit play, oh, right here, these guys, because we have our walkway. One of these guys has something attached to it, right?
Yep.
It's our board. Oh, I need to, if I'm going to remove him, I need to unclick that there, because when it was running, remember any changes you make during runtime won't be solid changes. All right, so let's look at this from a couple of different positions here. So here's our steps. Now, interestingly, our stair was here, yet it did position them relative to the view instead of the parent transform. That's actually an interesting thing to consider. I mentioned that anything that happens inside of this script is going to be relative to the parent's location, right? Instantiate seems to ignore that. So we actually need to, when we instantiate something, we do need to give it the parent transform as well. So let's see if there's a version of instantiate that will take in a position, a rotation, and a parent transform. And then I'll tell you what's going on there. So there's one that just takes the parent transform. That's not going to be good enough for us because we need to modify positions within there. There's our one that takes the parent and, this one will instantiate whether or not we want it in world space or not. The default is world space, it appears. All right, because we just saw all those guys start off at 0, 0 in world space and then count down, where we really want it relative to our anchor. So there's our vector 3 position rotation. So that's the one is defaulting to world space, creating an instance out of position relative to world space with our default rotation, well, with a rotation. Here's the one that takes in an original, a position, a rotation, and then the parent. So this will be the alternative to using world space, because we wanted to have a parent that is the owner of this script. So I'll use that third guy here. So I'm going to pass it this dot game object dot transform. You could also say this dot transform. That'll get you that same value, because for most of the things that deal with the game object that owns this script, this and this dot game object can be used interchangeably. But officially, this is the instance of a script. This dot game object is the instance of the game object that owns this script. So this dot game object dot transform would be the transform of the game object that owns this script, right? And this is going to be the parent transform of all the dudes that I'm instantiating. So this cur pos will be relative to this dude's position. That makes sense? So let's run this again and see if we get a little bit better looking staircase in the right position now. It's still in a weird position. I think it's in a weird position. Let's look at this guy relative. So that's on the Z. So it should definitely, yeah, that should be building it off of that, if that's the parent thing. So is there another one that we have to give it a true or false, whether it is world space? Like, even if we've given it a parent transform, do we still need to tell it that we want it in world space? So let's keep cooking. There are 10 of these. All right, so there's the guy we just used. That's going to be for instantiating a type. It's not going to get us there. Well, then, what we would do is we would say, instead of this being a vector 3, 0, we would say this dot game object dot transform dot position. So we would start our vector 3 off at the same position as our parent. we would not have to give it the parent transform since that didn't seem to help us at all. So now our first position will be at the exact same position as our parent's position. And as the game object that owns this position, and then we'll take steps from there. So this should put it in the right place. Just kind of wondering what's the purpose of a parent transform if it's not going to give you positions relative to that.
It did put steps under stairs. See how it's like not fair.
Okay, I get it. So yeah, so right here, stairs is its own empty game object. These guys were instantiated in the top level thing here when we did put it. So if we go back here and stop it and go into our code here, and we go ahead and tell it who our parent transform is. So that's this game object transform. It won't position it relative to that guy, but it will position it. It will make them a child of that guy. So now you can move this dude around, and all the stairs will come with it. So I guess that can be advantageous. I'm just a little surprised that it didn't. When you have a parent, it doesn't also let you do the position relative to that. So as he pointed out, notice all the steps are underneath the stairs now. So if I want to move stairs around, I can, and all of them will come with it. I can go to the scene here, and I can drag stairs over like this, and I can go back to the game, and the stairs are now moved over there. All right, so let's look at this again and do the stairs look kind of pretty close to where they should be. I'm looking at it on the Z here. I can't rotate that way on it, but it looks pretty reasonable, doesn't it? Where the stairs are. Okay, so we're going to call that a procedurally generated staircase, kind of ghetto style or something like that. Now, something we might want to do is we might want to let it choose whether or not the stairs are going to go up or go down, right? So how would we accomplish that? If I want to be able to tell my script whether I'm building stairs from my anchor point up or I'm building my stairs from my anchor point down, how would I represent that? How would you modify our current setup to accomplish that?
You just change the direction that like you can make like a new function like stairs up or something like that, and then just change the script how we had it like subtract.
How does it get called?
Whatever.
You got an idea, Jacob?
No.
You're not paying attention? So how does this go up or down? I mean, we could call a function. Yeah, I mean, so the ultimate logic is going to be whether or not we increase or decrease on this y, right?
Yeah.
But something needs to tell me, so I need some representation out here, that, a checkbox or something where I can say, I want this to be an up staircase or I want this to be a down staircase, something like that, right? I need that representation somewhere. So maybe a Boolean. Okay, so I can go in here and I can say public, that's bool in this language, public bool, and maybe should go down or something like that, should go down. And maybe I could default this guy to true. So when it's true, that means the staircase would go down, which is our default case here, right? So now, when we come back out here to Unity, we see that we get a text box or a little checkbox here that I can click on or click off. It's on right now, meaning that by default, we're going to have a staircase that's going to step down. If I uncheck this, our intention is we want a staircase that's going to step up, right? So what I'll do here is I can modify. How would I modify my code? So X is always going to change this way, right? The real difference is with the Y. So how do I modify this code to make it go either up or down depending on the should go down variable?
You change it to like if should go down is true, like have it do like the propose that Y like that, else if like copy the same thing but make it positive.
Okay, so if that is true, do that. Otherwise, add to it.
Yeah.
All right. So this is probably the most straightforward solution, right? Just ask the question. This goes back to our primitives of how do we program. We remember stuff, we ask questions, repetition. So if we want to conditionally do something, we're going to ask a question. Should I do this? If yes, do it. If not, do something else. All right, so we'll go in here. I have that saved. Right now, it's still checked. So we run this now, and it should be the down staircase. I'll uncheck it, run it again. Now it should be the up staircase, like that. Okay. Anybody have an alternative way we can write this? Kind of a shorter hand way. Not necessarily a better way, shorter hand way. Give you a hint. Inline if statement. I think everybody in here has seen those. We haven't necessarily used them a bunch. I think the guy in the video does use them, right? So an inline if statement, you remember the syntax for that guy is Boolean expression followed by a question mark, true expression, colon, false expression. What's a Boolean expression? Kind of animal. So what would you say to define a Boolean expression?
Something that boils down to yes or no.
Yeah, true or false, yes or no. Actually, there's only one language I can think of that actually uses yes or no. Do you know what language that is? I don't think you've used it unless you've used a language I'm not aware of.
I don't know.
So what made you say yes or no?
That's just what came to mind.
Those are the words. It's actually interesting. Objective-C. The original language you would have used for programming iPhone, and it's the old Mac language, Mac programming language, uses yes or no in place of true or false. Kind of interesting thing. And in some ways, you might, if you're thinking about programming, go back to our original definition of programming, where it's a power tool for allowing us to solve problems the way human beings already solve problems. Yes or no kind of makes more sense than true or false does, doesn't it? Like, is it sunny out? Yeah. it's sunny out. Instead of saying true, it's sunny out. You know what I mean? Similarly, we've the this keyword is something that's left over from do you know what language the this keyword came from? Did it come from C? It's a trick question. Actually came from C++. Why did it come from C++ but not C? What was the difference between C and C++?
Did C not have objects?
Yeah, C++ was the object-oriented version of C. So C didn't have objects, therefore no need for this keyword. Yep. So yeah, it came from C++. A language that isn't often used anymore. There's probably plenty of jobs that still use it because they have stuff written from years ago. But for a long time, this language was used pretty heavily because it was kind of a a hybrid language for jobs that weren't necessarily programming jobs, but that could use a level of kind of automation. And that was a language called Visual Basic. Probably all heard of that at some point at least. In general, Visual Basic was kind of considered to be maybe an easier language to program in. I'm not sure I agree with that because I still stand by the whole thing that all languages are the same. Visual Basic maybe was made you pay less attention to kind of code structure. That maybe is a true statement. And we still see some examples of this today where like Microsoft Access is still a thing, which is effectively a visual database that allows you to build forms and stuff for populating a database without really any programming experience or something, or putting very little programming stuff in there. But Visual Basic allowed you to be do a little bit more of a programming-y type thing. And if you, so I think you do this in 150. Do you do VBA, Visual Basic for Applications, when you're doing like Excel or something? Or in 175? Do you do any programming with spreadsheets in those classes?
Like Excel formulas.
Yeah, but that would be formulas built into it. There's you can also hang a script off of a cell that's written in something called VBA, Visual Basic for Applications. It's like a cut down version of Visual Basic. Visual Basic is a Microsoft language. Excel is a Microsoft product, so it kind of makes some sense, but you don't do any of that in those classes. Interesting. Wonder why. Bringing it up in our meeting today. What's this? Well, yeah. And that makes sense to do a little separate programming thing. Just, if you're looking at how can you use like a tool like Excel at more of a power level. Sometimes it would be handy to have some programming associated with the cell, like when you want to pull off something you really just couldn't have done with the formula. Every now and then that might be handy, especially if you're building really complex spreadsheets. But yeah, not a big deal, just more of an interesting thing. But where I was going with that is, the this keyword is kind of almost a weird thing to teach, right? Weird thing to understand until you just kind of get used to using it. But just referring to, the definition of this is, how an object refers to itself from within itself, right? The Visual Basic programming language, instead of this, used the keyword me. Kind of me. When that's how we think about it in real life, correct? When we're talking about us, we think about ourselves as me. So that's kind of I think a better term anyways. Just some trivia. Okay, but in any case, we can use an inline if statement here to accomplish this. So what we can do is we can say curpause. I can say plus equals or I can say minus equals. It doesn't matter what I say here. I just need to adapt my answers accordingly. So I'll say minus equals, and then I'll say this dot should go down. Then I'll put a question mark. So if should go down is positive, or is true, is yes, then I'll say I'm going to subtract 0.3f. Otherwise, I'm going to subtract negative 0.3f. Oh, and I don't want it to be curpause, period. I want it to be curpause.y. Okay, so if should go down is true, then we're going to boil down to 0.3f here, and that's what we're subtracting. Otherwise, we'll boil down to negative 0.3f here, so we're subtracting a negative, which is the same thing as adding. Right? So this should accomplish the same thing. So right now I should be going up. Run it again. Now it should be going down. All right, makes some sense? All right, so what other things might we programmatically generate in a world? I think last time I mentioned something about what if we wanted to programmatically generate this particular hallway, the computer science department, something like that. If you were to think about this department in terms of a collection of primitives, what are the things that make up the department?
Desks and chairs.
Okay, that's the stuff that's in it. True. Yeah, you're not wrong there. What about the rooms themselves, the hallways, that kind of stuff? How can we represent that? Assuming we don't want it to be hollow yet, how can we represent the rooms?
The walls, ceilings, and floors and stuff like that, and the layout of the room.
So could we like represent this room as a cube?
Yeah.
Generically, very generically, right? This room could be a cube. It's not hollow. We're not going to be able to put stuff in it yet, but we could represent this room as a cube. Okay, so, and could we represent that hallway as a cube?
Yeah.
We just need to stretch it out a little bit. So stretch it out, make it a little narrower so we can kind of give it some information about what that cube is, right? Okay, so what we can do, let's just start off by kind of like a little hobble into this. So we're going to create a script, and we're going to call this guy maybe cube modifier. Let's say that that's good. All right. And then for right now, I'm just going to get rid of my pretty much everything. So empty this guy out, and we'll go ahead and we'll throw a cube out here. And I will drag my cube modifier onto this cube. And we're going to go ahead and write some stuff here. So when we think about a cube modifier, what we really want to do is we want to give it a length, width, and a height, right? So whatever, let's do that. All right, so the length of a cube, so we got to think about this in terms of our dimensions. So length and width are going to be your x and your z. I'm sorry, yeah, x and z. So length might be x, z might be width, and then height is going to be your y. All right, so we're going to need 3 different inputs for this guy. So we'll say public float length. Let's see if this will work. Width, height. Just want to see if their version of MVC will work for doing this. So I'm going to capture these 3 pieces of information. And what I'll initially do is I'm going to default them all to 1. So we'll come back out to here. Click on my cube. Yep, it allowed me to put all of them under a single public line. I was wondering if how they implemented MVC was specifically going to expect 3 separate lines in here, because remember MVC is how our interface builder and our code link together. So when they wrote these systems, they had to kind of decide, well, how are we going to parse through the C# code and see what things do you want me to make those public fields in Unity? And it's entirely possible that they could have said for each word public they see here in the field category, I'm going to read 1 variable name. So they could have required 3 different public floats in order to get 3 variables like this. But they didn't, so this made life a little bit easier. All right, so we're going to hold on to those 3 different values there. Now, when we start, and we're effectively replacing the use of a transform, right? we're not adding a whole lot of value to this, other than just kind of giving ourselves a starting point. And I think that'll make sense here probably next time, but whatever. All right, so what we're going to do is we want to modify, if we're going to take in a length, width, and a height, and we want to adjust our cube to be that length, width, and height, what am I actually adjusting? What part of my cube do I need to adjust? Scale. So I need to just transform.scale. So I'll say this dot, I'm going to go ahead and say game object instead of just this dot transform. Well, let me say this dot transform here because that will match up to what the guy does in most of the code. This dot transform is synonymous with this dot game object dot transform. They're the same thing. Okay. So we'll say this dot transform dot scale. Now notice we have a couple of different things here. We have this thing called local scale, and we have something called lossy scale. This allows you to read the scale of something, and it rounds it. I think it's to 2 decimal places or something like that. When you need to do math with the scale of something, rather than you having something out to when you move something over a pixel, all of a sudden you have this giant 18 digits on the after the decimal point, and math becomes more complex and slower is the bigger thing. So sometimes you might do something with lossy scale. All right, so this dot, actually I want to try something here real quick. Yeah, so local scale is going to, so let me tell you how that guy works. It's kind of an important. Local scale. First, let me demonstrate it out here. Okay, so I'm going to create a cube, and I'm going to go ahead and I'm going to stretch this cube out a little bit so he's a little bit kind of oddly shaped. All right, so I have somewhat of an oddly shaped cube now. And then what I'm going to do is I'm going to, inside that cube, so as a child of this cube, I'm going to create another cube. And let me go ahead and drag that guy down a little bit. Notice that this cube does not look like a standard 1 by 1 by 1 cube, right? But look at his scale. His scale is 1 by 1 by 1. This guy's scale is 5.13 by 1.625 by 1. So this guy's scale, 1 by 1 by 1, is his scale relative to the parent transform, the dude he lives under. Does that make sense? So it is 1 by 1 by 1, which means it's a multiplier of 1 times the x on the scale of the parent, 1 times the y on the scale of the parent, 1 times the z on the scale of the parent. Make sense how that works? So local scale is a vector 3 representation of the relative scale of a game object. And this is relative to the parent transform. So transforms, and we saw this a few minutes ago with instantiate. And this is kind of a chicken or the egg type thing. So on the exam and several times in class, we've talked about this idea of what makes a game object the most generic game object, right? And we've said, oh, that's a transform. Now, we've thought about game objects, we've seen it over here where we've had things that are children of other things, right? So back over here in Unity, we have, a cube that now has a child that is a cube. So this cube is a child of this game object, right? So we would say this is a game object, this is a game object. So this game object that I have highlighted right here is actually a child of this game object right here. That's a fair thing to say. It's only almost true. This game object is actually a child of this game object's transform. So it's the transform that exists as a X, a Y, well, a position, a rotation, a scale, as well as a collection of 0 or more other transforms. And this is where chicken or the egg kind of comes in. Let me explain that. So if we were to expand our definition of a transform is a vector 3 position. It is a vector 3 rotation. And actually, it's not a vector 3 rotation. It's a quaternion rotation. And it's a vector 3 scale. We represent the rotation if we go back in here. Show you here real quick. I click on this guy. We see rotation. Our rotation we represent as a vector 3. Rotation about the X axis, the Y axis, or the Z axis, but under the hood it's actually represented as a quaternion. All right, but we can think of it as a vector 3 because that's what transform outwardly, publicly exposes it to us as. All right, so transform is a position, a rotation, a scale, as well as a collection of 0 or more transforms. Okay, and this is where the chicken or the egg thing comes in. When I put, back here, when I put this cube under this cube game object, we view this cube here as a game object. We don't think of that as a transform, right? It's a game object. It's a game object that happens to have a transform, but it's a game object. We could almost say, so if I said that the most generic version of a game object is a transform, must have a transform, it's equally accurate. In fact, in terms of implementation, it's more accurate to say a game object is a transform. Okay, so a game object with no additional components is a transform. Does that make some sense? All right, so if we start thinking about transforms as a collection of other transforms, where we're thinking of, okay, if this is a transform and we've put another game object in this guy, now his collection of 0 or more transforms includes this one game object or this one transform. Make sense? So at what point can we differentiate a transform from a game object? What's different between the two of them? I'm saying they're almost synonymous, right? But what can a game object have that a transform can't have? Other components, yeah. So we could have a collection of transforms, and we could actually get the game object that relates to that transform. We would look at it if we say a game object is a collection of components and one of those components is a transform, we can use a transform to get at the game object. Actually, let me show you. So if I say this dot transform dot, here's all sorts of things we can do relative to transforms. Notice that one of the things is this thing called Getcomponent. And we've used Getcomponent before, right? What have we used Getcomponent for? To get a component of a game object. Okay, but we're working with a transform here. So a transform and a game object are tightly knitted. So when I say this dot transform dot GetComponent, I'm getting the component of the game object that owns this transform. You see how it's taking those steps for us? Instead of me saying, this dot transform, tell me about your game object, which I can do. So notice the game object component of a transform is the game object this component is attached to. A component is always attached to a game object. So we would say that a transform by definition is a component, saying that here. But we can use that component to ask about his parent. We can ask a transform to tell us about the game object that owns him. Does that make sense? So these two are really tightly coupled. And it's actually part of what makes Unity work. Because we can almost say that in Unity, this idea of a game object, just like in any other object-oriented programming language, any object-oriented programming language, we would say that in order to get the ball rolling, so to speak, they must have a generic object, maybe called object. In Java and C#, it's called object, as well as in Swift. In Objective-C, it's called NS object. C++ is called object. What's it called in C? Another trick question. C doesn't have objects, right? So we don't have that version in C. All right, so in any case, when we look at the programming language side of things, we always have a starting point. And in order to have the inheritance model off of that, to have a hierarchy underneath that. Same thing's true now on kind of the programming liaison of Unity as it talks to the C# language. We have this top level primitive called a game object. And a game object in its most basic form has a transform, but in a lot of our situations, in order to make logic work, it uses game object and transform synonymously, okay, where they're basically the same thing. That makes some sense? All right, so we can use a transform to get at a game object. We can also use a game object to get at a transform. There's some kind of circular thing there, so you can actually get stuck. So we can say this dot game object dot transform dot game object dot transform dot game object and so on and so forth. Isn't that fun? So you can create an infinite loop. Well, potentially an infinite loop. Just dealing with the game object of the transform, you can probably write some sort of loop that says as soon as the last transform you looked at is different than the next transform, but it's still the same transform. Yeah, things will break. Okay. So transforms, maybe in parentheses game objects. Then we can have a slide that says game object, maybe in parentheses called transforms. We could also think of them as a collection of 0 or more transforms, and we can throw game objects, in our in parentheses there or something. All right. I wouldn't ask you like on a test or something to give me a real clear differentiation between the two of them. So you can almost use those two words interchangeably because they're purposely making it ambiguous, as we just saw by this dot game object dot transform dot game object dot transform dot game object. These are the same things to a certain extent. Okay. But in any case, we want to think about these guys as collections of things because sometimes that makes a difference. And we're seeing it here in the context of the transforms, this guy's transform scale component, scale subcomponent, is a 1 by 1 by 1, which historically, if I go and I create a cube out here, so here's a cube that has a scale of 1 by 1 by 1. Here's a cube that has a scale of 1 by 1 by 1. Yet they don't look like the same cube, do they? Go ahead.
If you change the parent, I'm just wondering, if you change the parent, like the scale of the parent, does that change the numbers of the second?
That's a good question. I think it will. You mean if I change the scale of this one?
Yeah.
Well, it should, because this guy is a multiplier based on the parent. So this guy's scale on X is 1 times the scale on X of the parent. So if I change the parent to a 10, because it's a calculated, scale is going to be calculated. It's based on the scale of his parent.
Okay.
Make sense? Okay, so that's kind of an interesting, sometimes confusing thing, where if I look at this cube and he has a scale of 1 by 1 by 1, and I look at this cube and he has a scale of 1 by 1 by 1, and I look at those cubes right next to each other, and one is a pretty fat cube and one of them is not so much of a fat cube, right? They are definitely different geometric cubes, but they both have the same scale. This changes our understanding of scale a little bit, right? So if we talk about scale, just real quick here, I know we're out of time. Scale is an X, Y, Z scale relative to the scale of the parent transform, or world space if there is not a parent. That makes sense?
You take it out of the parent.
It won't initially. Yeah, so if well, actually, I get what you're saying. Will it change the actual scale numbers? It does, but it still kept its size to where it was before. But its scale numbers are now relative to world space. That's why the numbers jumped. But yeah. It makes sense? Questions, comments, concerns, bribes? All right. I will see everybody on Tuesday. Remember, the assignment is up. So is the Bible homework that's due midnight on Sunday or 11:59 on Sunday. Plenty of room in the front row of chapel. I'll see you up there.